formula voltage drop equals 1.73 times the current times the distance times the AC resistance factor is used to calculate voltage drop on alternating current cables. The AC resistance factor value in this formula depends on the conductor material, insulation material, and cable construction. For 15 kilovolt cables, the AC resistance factor value is typically higher than that of 600 volts cables due to increased insulation thickness and different conductor materials. National Electrical Code Chapter 9 Table 8 does not provide AC resistance factor values for 15 kilovolt cables specifically, but it can be estimated based on the following factors. Firstly, the conductor material. 15 kilovolt cables typically use copper or aluminum conductors. The AC resistance factor value for copper conductors is lower than that of aluminum conductors. Secondly, insulation material. 15 kilovolt cables often use cross-linked polyethylene or ethylene propylene rubber insulation. The AC resistance factor value for cross-linked polyethylene insulation is lower than that of ethylene propylene rubber insulation. Thirdly, cable construction. The AC resistance factor value is also affected by the cable construction, such as the number of conductors, the spacing between conductors, and the presence of a metallic sheath. Based on these factors, the AC resistance factor value for 15 kilovolt cables can be estimated to be in the range of 0.25 to 0.40 ohms per 1000 feet. However, it's important to note that these are approximate values, and the actual AC resistance factor value may vary depending on the specific cable characteristics. To determine the precise AC resistance factor value for a specific 15 kilovolt cable, it's recommended to consult with the cable manufacturer or refer to industry standards such as the Insulated Cable Engineers Association or the National Electrical Manufacturers Association. When calculating voltage drop in electrical systems, especially for medium voltage applications such as 13.8 kilovolt systems, understanding the factors that influence cable impedance is crucial. The AC resistance factor, often denoted as AC resistance factor, plays a significant role in determining the overall voltage drop in a cable run. Unlike direct current resistance, which is relatively straightforward to calculate, alternating current resistance takes into account the skin effect and proximity effect, which increase the effective resistance of the conductor at higher frequencies. The skin effect causes alternating current to flow primarily on the surface of the conductor, reducing the effective cross-sectional area and increasing resistance. The proximity effect, on the other hand, is caused by the magnetic fields of nearby conductors, which can further distort the current distribution and increase resistance. For 13.8 kilovolt cables, which operate at medium voltage levels, the AC resistance factor can be significantly higher than the direct current resistance, especially for larger conductors. This is because the skin effect and proximity effect become more pronounced as the conductor size and frequency increase. Therefore, it's essential to use the appropriate AC resistance factor value when calculating voltage drop in these systems. Several factors influence the AC resistance factor of a cable, including the conductor material, conductor size, conductor stranding, insulation material, operating temperature, and frequency. Copper and aluminum are the most common conductor materials used in electrical cables, and each has its own unique properties that affect the AC resistance factor. Copper has a lower resistivity than aluminum, which means it offers less resistance to the flow of electrical current. As a result, copper conductors typically have a lower AC resistance factor than aluminum conductors of the same size. The size of the conductor also plays a significant role in determining the AC resistance factor. Larger conductors have a lower direct current resistance, but the skin effect and proximity effect become more pronounced as the conductor size increases. This means that the AC resistance factor increases with conductor size, especially at higher frequencies. Conductor stranding also affects the AC resistance factor. Stranded conductors are made up of multiple individual wires that are twisted together to form a single conductor. This construction increases the surface area of the conductor, which can reduce the skin effect and lower the AC resistance factor. The type of insulation material used in a cable can also affect the AC resistance factor. Some insulation materials have a higher dielectric constant than others, which can increase the capacitance of the cable and affect the current distribution. This can lead to a higher AC resistance factor, especially at higher frequencies. The operating temperature of the cable also influences the AC resistance factor. As the temperature of the conductor increases, its resistance also increases. This is because the increased thermal energy causes the atoms in the conductor to vibrate more, which impedes the flow of electrons. The frequency of the alternating current also affects the AC resistance factor. As the frequency increases, the skin effect and proximity effect become more pronounced, leading to a higher AC resistance factor. In order to accurately calculate voltage drop in 13.8 kilovolt systems, it's essential to obtain the appropriate AC resistance factor value for the specific cable being used. Cable manufacturers typically provide this information in their product catalogs or technical data sheets. These values are usually determined through testing and are specific to the cable's construction, materials, and operating conditions. If the AC resistance factor value is not readily available, it can be estimated using various formulas and tables provided in industry standards such as the National Electrical Code, the Insulated Cable Engineers Association Standards, and the National Electrical Manufacturers Association Standards. These resources provide guidance on calculating the AC resistance factor based on the cable's characteristics and operating conditions. In addition to the AC resistance factor, other factors that must be considered when calculating voltage drop in 13.8 kilovolt systems include the cable's reactance, the load current, and the distance of the cable run. Reactance is the opposition to the flow of alternating current caused by the cable's inductance and capacitance. Inductance is the property of a conductor that opposes changes in current flow, while capacitance is the ability of a conductor to store electrical energy. The load current is the amount of current flowing through the cable, which is determined by the power requirements of the connected equipment. The distance of the cable run is the length of the cable from the source to the load. The longer the cable run, the greater the voltage drop. To calculate the voltage drop in a 13.8 kilovolt system, you can use the following formula: voltage drop equals 1.732 times the current times the impedance times the length divided by 1000, where 1.732 is the square root of 3, which is used for three-phase systems. The current is the load current in amps, the impedance is the cable impedance in ohms per 1000 feet, and the length is the cable length in feet. The cable impedance can be calculated using the following formula: impedance equals the square root of resistance squared plus reactance squared, where resistance is the AC resistance of the cable in ohms per 1000 feet, and reactance is the cable reactance in ohms per 1000 feet. By using these formulas and considering all of the relevant factors, you can accurately calculate the voltage drop in a 13.8 kilovolt system and ensure that the connected equipment receives the proper voltage. This is essential for maintaining the reliability and efficiency of the electrical system. When selecting cables for 13.8 kilovolt applications, it's important to choose cables that are specifically designed for medium voltage use. These cables typically have thicker insulation and are constructed with materials that can withstand the high electrical stresses associated with medium voltage systems. It's also important to ensure that the cables are properly installed and terminated to prevent insulation breakdown and other potential problems. Proper installation practices include using the correct cable supports, maintaining proper spacing between cables, and using the appropriate termination kits. In addition to selecting the right cables and ensuring proper installation, it's also important to perform regular maintenance and testing to detect any potential problems before they lead to failures. This includes visual inspections, insulation resistance tests, and partial discharge tests. Visual inspections can help identify any signs of damage or degradation to the cable insulation. Insulation resistance tests can measure the resistance of the cable insulation to detect any weaknesses or defects. Partial discharge tests can detect the presence of small electrical discharges that can occur in the cable insulation, which can be an indication of impending failure. By performing regular maintenance and testing, you can extend the life of your 13.8 kilovolt cables and ensure the reliable operation of your electrical system. In summary, calculating voltage drop in 13.8 kilovolt systems requires a thorough understanding of the factors that influence cable impedance, including the AC resistance factor, reactance, load current, and cable length. By obtaining the appropriate AC resistance factor value, using the correct formulas, and considering all of the relevant factors, you can accurately calculate the voltage drop and ensure that the connected equipment receives the proper voltage. It's also important to select cables that are specifically designed for medium voltage use, ensure proper installation, and perform regular maintenance and testing to prevent failures and maintain the reliability of your electrical system. When working with medium voltage systems such as 13.8 kilovolt installations, it's crucial to adhere to all applicable safety regulations and codes. These regulations are designed to protect workers from electrical hazards and ensure the safe operation of the electrical system. Some of the key safety regulations and codes to be aware of include the National Electrical Code, the National Electrical Safety Code, and Occupational Safety and Health Administration regulations. The National Electrical Code provides comprehensive guidelines for the safe installation and maintenance of electrical systems. The National Electrical Safety Code covers the safety aspects of electrical supply and communication lines, equipment, and associated work practices. Occupational Safety and Health Administration regulations establish workplace safety standards to protect employees from hazards such as electrical shock and arc flash. When working on 13.8 kilovolt systems, it's essential to use appropriate personal protective equipment such as insulated gloves, safety glasses, and flame-resistant clothing. It's also important to follow lockout-tagout procedures to de-energize the equipment before working on it. Lockout-tagout procedures involve disconnecting the power supply to the equipment and placing a lock and tag on the disconnect switch to prevent it from being accidentally re-energized. In addition to following safety regulations and codes, it's also important to receive proper training before working on 13.8 kilovolt systems. This training should cover topics such as electrical safety, lockout-tagout procedures, and the proper use of personal protective equipment. By adhering to all applicable safety regulations and codes, using appropriate personal protective equipment, and receiving proper training, you can minimize the risk of electrical hazards and ensure the safe operation of 13.8 kilovolt systems. Furthermore, consider the impact of harmonic currents on voltage drop calculations. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as variable frequency drives, electronic ballasts, and uninterruptible power supplies. These harmonic currents can distort the voltage waveform and increase the overall current flowing through the cable, which can lead to increased voltage drop. To accurately calculate voltage drop in systems with harmonic currents, it's important to use a harmonic load flow analysis tool. These tools can simulate the flow of harmonic currents through the electrical system and calculate the resulting voltage drop. In addition to using a harmonic load flow analysis tool, it's also important to consider the directing factors for cables that are exposed to harmonic currents. Directing factors are used to reduce the ampacity of cables to account for the increased heating caused by harmonic currents. The directing factors for harmonic currents are typically provided in cable manufacturers' catalogs or technical data sheets. By considering the impact of harmonic currents and using appropriate directing factors, you can ensure that the cables are properly sized and that the voltage drop is within acceptable limit. Another important consideration when calculating voltage drop in 13.8 kilovolt systems is the effect of unbalanced loads. Unbalanced loads occur when the current flowing through each phase of the three-phase system is not equal. This can be caused by single-phase loads, such as lighting and small appliances, being unevenly distributed across the three phases. Imbalanced loads can cause voltage imbalances, which can lead to increased voltage drop and equipment overheating. To minimize the effects of unbalanced loads, it's important to balance the loads as much as possible across the three phases. This can be achieved by carefully planning the distribution of single-phase loads and using load balancing transformers. Load balancing transformers are designed to redistribute the current flow between the phases to reduce the voltage imbalance. In addition to balancing the loads, it's also important to use a voltage imbalance monitoring system to detect any excessive voltage imbalances. These systems can provide an alarm if the voltage imbalance exceeds a predetermined threshold, allowing you to take corrective action before it leads to equipment damage. In summary, calculating voltage drop in 13.8 kilovolt systems requires careful consideration of several factors, including the AC resistance factor, reactance, load current, cable length, harmonic currents, and unbalanced loads. By understanding these factors and using appropriate calculation methods, you can ensure that the voltage drop is within acceptable limits and that the electrical system operates reliably and efficiently. Also note that the NEC provides guidance on voltage drop in informational note number 2 to section 210.19. This informational note indicates that the voltage drop should not exceed 3% for branch circuits and 5% for feeders plus branch circuits. These are recommendations, not mandatory requirements, but adhering to these guidelines will likely lead to better performance and efficiency of the electrical system. Voltage drop calculations are important not only for safety but also for economic reasons. Excessive voltage drop can cause equipment to operate inefficiently, leading to increased energy consumption and higher electricity bills. It can also shorten the lifespan of equipment and increase maintenance costs. By properly calculating voltage drop and selecting the appropriate cables, you can minimize these costs and ensure that your electrical system operates at peak efficiency. To further enhance your understanding of voltage drop calculations, consider using software tools that can automate the process. Several software packages are available that can perform voltage drop calculations based on various input parameters, such as cable size, load current, and cable length. These tools can save you time and effort and help you ensure that your calculations are accurate. Some software tools also provide features such as cable sizing recommendations and harmonic load flow analysis. When using software tools for voltage drop calculations, it's important to verify the accuracy of the results by comparing them with manual calculations or published data. This will help you ensure that the software is functioning correctly and that the results are reliable. In addition to software tools, there are also online calculators available that can perform voltage drop calculations. These calculators are typically free to use and can be a convenient way to quickly estimate the voltage drop in a circuit. However, it's important to note that online calculators may not be as accurate as software tools and should be used with caution. When using online calculators, be sure to input all of the required parameters accurately and to verify the results with other sources. Finally, remember that voltage drop calculations are just one aspect of electrical system design. It's also important to consider other factors such as cable ampacity, short-circuit current rating, and grounding requirements. A well-designed electrical system will meet all of these requirements and provide safe, reliable, and efficient power to the connected equipment. The goal is to ensure the correct and safe functioning of any electrical equipment. In summary, accurately determining the AC resistance factor and performing meticulous voltage drop calculations are vital for ensuring the efficiency, safety, and regulatory compliance of 13.8 kilovolt cable systems. Consulting manufacturer specifications and adhering to established industry standards are crucial steps in achieving optimal system performance and longevity.